This video is about analysis and characterization of linear time invariant systems using Laplace transform. So previously we have analyzed and characterized using the time domain techniques, but right now we will be looking into the Laplace domain to understand linear time invariant systems. So specifically for the time domain, we know that the output y of t is equivalent to the input x of t and convolution of x of t with the impulse response, that is h of t, where this is the convolution operator. But in the S domain, using the convolution property, Laplace transform of the output, that is y of s, so this is equivalent to the Laplace transform of the input x of s and the Laplace transform of the impulse response, that is h of s, right? So this h of s is something that we call as transfer function or a system function. Previously, we were able to analyze any given linear time invariant system by means of an impulse response h of t. So same can be done in the S domain by means of the transfer function h of s. So presently we will be looking into two properties, that is causality and stability, and we would determine causality and stability by means of the transfer function h of s. So let us first look into causality. In time domain, we said that a system having an impulse response h of t and the system is linear time invariant system, right? So if this system is 0 for t less than 0, so this means that the system is causal. So we can determine the causality by means of a transfer function as well, that is h of s can be used to find the causality of a given system. Specifically, we have two definitions. The first one is that the region of convergence associated with the system function or a transfer function for a causal system is right half plane. Also, we can say that for a system with a rational system function, causality of system is equivalent to the region of convergence being to the right half plane to the right of the rightmost pole. So the statements look a little bit confusing at first, but they are very straightforward. So let us understand and analyze the causality of a given system with the help of some examples. So let us say we have a linear time invariant system which has an impulse response h of t equivalent to e minus at u of t. So we know that the Laplace transform of this function, that is h of s, is simply 1 over s plus a, and the real part of s is greater than minus a. So that is a function in time domain is causal. It is starting from 0 and it is right sided. So at the same time, in terms of the region of convergence, we have a pole at minus a and the ROC is to the right of it. But let us say we have another transfer function. So this is h2 of s, and this is equivalent to 1 over s plus a, and again the real part of s is greater than minus a, but this time we are multiplying it with e raised to power s. So if we are multiplying e raised to power s, then from the time shifting property, we can have h2 of t, which will be simply e minus a, and then we have a 1 here, so this will become t plus 1 times u of t plus 1. Now this signal is clearly not causal because it is not satisfying this condition. But again, this is right-sided. This was also right-sided. So the second definition says that this has to be rational. If it is rational and ROC is to the right of rightmost pole, only then it is causal. Otherwise it is not causal. So since this is not a rational function, since in the denominator we do have a polynomial form, but in the numerator it is not in a standard polynomial form, so this is not a rational function. So in short, if the function is rational and the region of convergence is towards the right of the rightmost pole, then the system is definitely causal. Otherwise it is not. So we can say that all causal signals, they would have a right-sided region of convergence. But at the same time, the reverse is not always true. So as we can see that over here, the region of convergence was towards the right of rightmost pole, but at the same time, the system is non-causal. The second property deals with stability of linear time invariant systems. And we need to determine the stability by means of the transfer function h of s. So by definition, an LTI system is stable if and only if the region of convergence of its system function h of s includes the entire j omega axis. That is, for real part of s, the value is equal to 0. So what this means is that we can have an S-plane, and this definition states that the j omega axis should be covered when sigma is equal to 0. So if this is the case, then the system is stable. Otherwise it is unstable. So let us understand this with help of 3 different cases of the region of convergence. And say for all of these cases, the system function h of s is equal to 1 over s plus 1 and s minus 1. So that means we have a pole at minus 1 and plus 1. Now the ROC can be in 3 different forms. You can have an ROC which is towards the right of rightmost pole. We can have an ROC which is in a strip between the 2 poles, and we can have an ROC which is to the left of leftmost pole. So based on the aforementioned condition, only the second case is satisfying the condition that the entire j omega, the imaginary axis, is being covered, right? So this is being covered in only the second case. So this means that only the second case is stable, where in the first case this is not covered, and in the third case this is also not covered. So 1 and 3 are unstable. Also note that we can determine the causality of this kind of a function, since this is a rational function. So if the region of convergence is towards the right of rightmost pole, so this means that the system is causal. So this is unstable and causal. Over here, the region of convergence is not towards the right of rightmost pole in the second case. This is stable but not causal. And lastly, the third case, this is unstable and also not causal. So let us say we have a linear time invariant system. Specifically, we have a second order circuit that is an RLC circuit. And which is at initial rest. So let us understand for this kind of a system or a circuit, how can we find the system function h of s, and how we can infer causality and stability for the system. So say our circuit is having a voltage source, say x of t, and then we have an inductor followed by a resistor and a capacitor. So the value of inductor is 1 Henry and the resistor value is 3 ohm and capacitance is 1 by 2 farad. And we are interested in the output current that we term as y of t. So as a first step, we can use the KVL, and from that, voltage across the inductor plus voltage across the resistor plus voltage across the capacitor would be equal to the input voltage x of t. So next, using current laws, we would have d by dt y of t. So because inductor value is 1 Henry, so we simply say d by dt y plus 3 y of t plus 1 over c, so it would be 2 minus infinity to t y of tau d tau. So this is equivalent to x of t. So next we convert this into an all differential form, that is we are differentiating both sides. So in that case we would have d by dt double derivative y plus 3d by dt y plus 2y of t equal to d by dt x of t. So next, in the fourth step, we would be taking the Laplace transform of this expression in 3, and then we'll be using differentiation in time domain to convert d by dt to its counterpart. So hence this y by taking Laplace transform, so from time domain we will go to s domain, so we would have y of s, and moreover this d by dt, so if we are differentiating in time, so this means that we are multiplying in the s domain. So since we are differentiating twice, so we would be multiplying twice with the polynomial s, so this will become s square y of s. Similarly, this will become 3s y of s plus 2y of s, and this will be equivalent to sx of x. So from a differential form in 3, we have reached a linear equation in step number 4. So this would assist us in determining the transfer function or the impulse response of this circuit. So taking y of s common, we have s square plus 3s plus 2, and this is equal to sx of s. But note that from convolution property, y of t was x of t convolved with h of t. So we have y of s, x of s, h of s. So this means that h of s is equal to y of s over x of s. And as from here we simply have s over s square plus 3s plus 2. So this is our transfer function. or we can take the roots of denominator, so we can have s plus 1 and s plus 2, and by taking partial fraction expansion, so this would be equal to 2 over s plus 2 minus 1 over s plus 1. Now from this equality over here, we know that in the s plane we have a pole at minus 1, another pole at minus 2, and a 0 at the origin. So since the ROC is not mentioned over here, so we could have three different cases of ROC. So this is our first case in which the ROC is towards the rightmost pole. Then we can also have a case, again we have a 0 at origin, minus 1 and minus 2, and the ROC is in the strip. Lastly, we can have an ROC towards the left of leftmost pole. So let us try to find the impulse response h of t and determine the causality based on these three cases. So just by inspection, we know that h of s over here is a rational function, and in the first case the ROC is towards the right of rightmost pole, so this is definitely causal. This is just by inspection. At the same time, since the ROC is not towards the right of this pole, in the second case minus 1, so this is not causal. And similarly this is also not causal. So let us come back to the first case itself. So in this case, the region of convergence for this should be greater than minus 2, because for this particular term the pole is at minus 2, so ROC would be towards the right of minus 2, and for this the ROC would be towards the right of minus 1. So in this case we have this ROC which is mentioned over here. Therefore, using pair 6, h of t would be equal to 2 times e minus 2t u of t, and then minus e minus t u of t. So this is our impulse response, and we can observe that this is causal because this is right-sided and this is also right-sided. Also we note that this is converging, so it would be stable, and from the transfer function h of s, it is covering the geometric axis, so from the transfer function itself we can also find that this is stable. Note that we have already found this solution in the time domain techniques, the link of which is given in this card. Now let us move towards the second case, which is over here. So in this case, this is indicating that the real part of s is greater than minus 2. So again this is not changing, but at the same time over here real part of s is less than minus 1. So hence we would have h of t equivalent to 2e minus 2t u of t, and using pair 7, that is we would have minus e minus at u of minus t, so this would become plus, and we would have e minus t u of minus t. So hence this is both sided and it cannot be causal, and we have already determined it. It is also unstable because if we plot h of t, so this would be converging in time domain, but at the same time this is expanding as we go towards minus infinity in time, so it is unstable. Now for the third case, over here the real part of s would be less than -2 to have this ROC, and similarly the real part of s should be less than -1, so it would be from here to the left. So as in this case we would have plus e minus t u of minus t, and also minus 2e minus 2t u of minus t. But note that since the value of inductor, resistor and capacitor is positive, so in this case the system is always going to be causal, and it would be stable as well because the poles will be towards left of it and it would be right sided. So note that in this example we have moved from 3 to 4 for a second order circuit or a system. So let's say we have an nth order differential equation. So we can mathematically express this, say if this is having an order of n, right, and we're using a variable k to identify a given component or given term. So the differential would be with respect to this variable k, y of t equal to the order of differential on the right side. So say that order is m, and again k is equal to 0 by dt k x of t. But also we have these constant coefficients, so let us call them alpha k and beta k. So this is a standard formulation which we call as linear constant coefficient differential equation. That is LCCDE. So in the example we took the Laplace transform and used the time differentiation property on this expression. So similarly for the general form we can again use the Laplace transform and the differentiation property to get another generic form, which is again k equal to 0 to n alpha k, and the differential changes to the power of polynomial sk y of s, and similarly this is k 0 to m beta k sk x of s, and from here the standard formulation of transfer function originates, which is simply k equal to 0 to m beta k sk over a summation k equal to 0 to n alpha k sk. So these identifies the zeros and then these identifies the poles.